Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at two special types of maps, homomorphisms and isomorphisms. Let's start with homomorphisms. Well, this word literally means a similar shape or structure. Homomorphisms are structure-preserving maps. I'll show you what I mean by that in a second. But we're just looking at homomorphisms between two groups, G and H. So this just says F is the map from a group G to another group H. Now, in order for the map to constitute a homomorphism, it has to satisfy this property here. So what exactly is this saying? It's saying that under this map, it doesn't matter if you perform the operation first in G, then map it, you will get the same outcome as if you map each of the elements individually and then perform the operation in H. Now note here, this and this denote arbitrary operations. They can be different. For example, this could be multiplication and this could be addition. So let's look at an example of a homomorphism and hopefully understand why they're important. So here we're defining a map F. It maps from the set of integers under addition, which is a group, to the set of integers modulo 5 under addition. The map is explicitly defined here. This just says it takes a number to its residue modulo 5. So let's show that this is an additive homomorphism. It is a homomorphism where both of these operations are addition. So let's take two integers x and y and let's look at what happens under the map. So f of x plus y will be mapped to the residue of x plus y mod 5. But what if we map each of these elements individually first? We have f of x, that's the image of x. We have f of y, the image of y, and then we add them. So we would get x mod 5 plus y mod 5. So we already know that these two are equal. It doesn't matter whether you add integers first then reduce modulo 5 or you reduce each integer modulo 5 and then add them. As a concrete example, let's say I wanted to map 8 plus 10 in modulo 5. Well, that's the same as mapping 18 and that reduces to 3 in mod 5. But if I map 8 first, then I map 10 and add the two answers, well, 8 is equivalent to 3 mod 5, 10 is equivalent to 0 mod 5, so their sum is equivalent to 3 plus 0, which is 3 mod 5. So when I said before that this preserves structure, it means basically that the things that work here work exactly the same way in the second group. When we're performing such a map, we're really saying we don't care about the properties of a number, we only care about what that number reduces to modulo 5. And we know that all the numbers that have the same residue modulo 5, so for example 3, 8, 13 or whatever, they all really behave the exact same way in this group here, modulo 5. They're all equivalent to 3 mod 5, and that is preserved by this map. It really maps all of these elements that do exactly the same thing to one element. In this case, all of these would be mapped to 3 mod 5. It really maps all of the ones that do the same thing to the same element in the second group. All right, let's now look at a non-example of a homomorphism. So here we have a map between two groups. So this is the group of non-zero integers under the operation multiplication. And this set here has two elements. It forms a group also under multiplication. So the map from this first group to the second group is defined here. It maps all even integers to this element and all odd integers to that element. So it's definitely a map between groups, but it's not a homomorphism. So to see this, we can easily find a counterexample. So what would happen under this map to say an integer like 21? Well, 21 is clearly odd, so it will be mapped to -1. But we know that 21 is, of course, 3 by 7. So f of 3 by 7 is the same as f of 21. But if I were to map these individually, so let's map 3 and let's map 7 and see what would happen when we combine them in this set here. Well, 3 would be mapped to -1. 7 would be mapped to -1 because they're both odd. But -1 times -1 is 1. This fails the definition of a homomorphism. You can see clearly under this map, it matters whether or not we map the elements individually, then combine, or we combine first and then map. So why is this a problem? Well, it doesn't preserve the structure. See, in this first set, which was the set of non-zero integers under multiplication, see, we know that when you multiply an odd by an odd, you get another odd. That's just common sense. But the problem is, in this set here, odd numbers, which are all equivalent, all mapped to -1, if you have an odd times an odd, you get in the second set -1 times -1, you get +1, which is even. So it hasn't preserved this structure. This clearly is nonsense. Because the map wasn't a homomorphism, we can see that there was structure, there were properties of numbers under certain operations that are just not true anymore. So that's why homomorphisms are important. We want to avoid situations like this. So let's take a second now to look at the kernel. So here we have a map F. We're going to look at the kernel of a homomorphism. So F is going to be a homomorphism from a group G to another group H. So the kernel of the map is just the set of all elements of G that are mapped to the identity in H. And that's exactly what this says here in set builder notation. So let's return to our homomorphism from the integers to integers modulo 5. Both of these under the operation of addition are groups. So we have the same map that we had before. So what would be the kernel of this homomorphism? We saw before that it was a homomorphism. Well, we're looking for all of the integers, so these are the normal integers, that are mapped to the identity in mod 5. Now, because we're looking at the operation of addition, the identity in this set is 0. 0 is the additive identity. So we're looking for all of the integers that under this map would be mapped to 0. So which numbers, when you reduce modulo 5, end up in 0? Well, they're precisely the multiples of 5. So the kernel of this map, denoted ker F, that will just be the set of all multiples of 5. So in set builder notation, we would just write it as 5 times some number n, where n is an integer. Any integer that satisfies this, i.e. is a multiple of 5, will be mapped to 0 under this map. So of course, that would include the number 0. It would include many more as well. So these dots mean it goes forever. It would include -5, 0, +5, +10, and so on. All of these are in the kernel. Now, it's important here that 0 is in the kernel. One important property of homomorphisms, they always map the identity of the first set to the identity of the second set. They always map inverses to inverses. That's part of their structure preserving properties. All right, let's now look at isomorphisms. So we've already looked at homomorphisms. If you have a homomorphism between these groups G and H, it is called an isomorphism if it is also bijective. So an isomorphism is just a bijective homomorphism. And if you can find an isomorphism between these two groups, we say that they're isomorphic, which basically means the same shape. Two sets that are isomorphic are basically the same. So let's look at some isomorphic groups here. So first is C4. This is the cyclic group of order 4. So it has 4 elements, and it has also this property x to the power of 4 equals 1. So the cyclic groups like this, they're groups under multiplication. It turns out that this group is isomorphic to the set of units, that is the set of non-zero elements in modulo 5, also under multiplication. Now, of course, we haven't included 0 here because 0 doesn't have a multiplicative inverse, and a requirement for a group is that each of its elements has an inverse under the group operation. So an isomorphism is defined by this function here. So basically it's saying we take whatever the power is of the element in this group and we map it to 2 to the power of that number in modulo 5. So let's look at how the map would work. So here the power is 0. 1 is the same as x to the power of 0. So what we do under this map is we take the power and raise 2 to that modulo 5. So 2 to the power of 0 is 1 modulo 5. So this element's mapped there. This is x to the power of 1. It gets mapped to 2 to the power of 1, which is 2 mod 5. Here the power is 2. We map it to 2 squared, which is 4 modulo 5. Now here the power is 3, map that to 2 to the power of 3, which is 8, equivalent to 3 in modulo 5. So this map here is clearly a bijection. There is a 1-to-1 correspondence between elements of the first set and elements of the second set. But let's verify that this is, in fact, a homomorphism. So let's see what happens if we combine elements of the first group. So if I want to map this here, what I would end up doing is multiplying x to the power of m by x to the power of n. You know that when we multiply bases, we keep the same base and add the powers. So under this map, this would just be mapped to 2 to the power of m plus n and then reduced modulo 5. So what if we mapped them individually? So if we map x to the power of m and x to the power of n separately, we would end up with 2 to the power of m, that would be this. This would be mapped to 2 to the power of n. We'd end up with the exact same result, 2 to the power of m plus n modulo 5. So that shows that our bijective map is indeed a homomorphism and therefore it's an isomorphism. So what happens here is the element here and its corresponding element here, they behave in the same way. These two do the same thing in both sets. 2 in this set does the same as x in this set. So what do I mean do the same? Like they have the same order, they have the same properties. For example, in this set, these two are inverses. 2 times 3 gives you 1 in mod 5. And it turns out in this set, these two are inverses. If you multiply these two, you get x to the power of 4, which is 1. So each element here behaves the same as its corresponding element here. So what about this set here? It turns out this set, which is integers modulo 4 under addition, it is isomorphic to this set as well. So let's try and find a homomorphism from this group to this group. Now the obvious one is f of t is t plus 1. I just take the element in this group and add 1 to it. So what would happen under this map? 0 would be mapped to 1, 1 to 2, and so on. Now this is clearly a bijection, but it's not actually a homomorphism. The reason it's not a homomorphism, it doesn't preserve structure. These two elements have been mapped to the wrong elements in this set. As an example, in this set, we already said these two are inverses, but in this group, these two are not inverses. 1 plus 2 doesn't give you 0 in mod 4. In fact, these two are inverses. So we need to find a map that doesn't go like that. It needs to map 0 to 1 and 1 to 2. That part was right, but we need it to map 2 to 4 and 3 to 3. It turns out that this here is a homomorphism. If we follow this rule, we will get the map here in green. 2 will be mapped to 2 squared, which is 4 mod 5. 3 will be mapped to 2 to the power 3, which is 3 mod 5. For example, this element needs to be multiplied by itself 4 times to get the inverse. 3 to the power of 4 is 1 in this group, whereas in this group, this one needs to be added to itself 4 times in order to get the identity, which is 0. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.